Good afternoon. So for those of you who don't know me, I work in Daniela De Angelis's research group at the MRC Biostatistics Unit in Cambridge. And our group works mainly on developing statistical methods for evidence synthesis in infectious diseases, not just flu, motivated very much by the public health problems in infectious disease. So when Mark asked us to give a talk on evidence synthesis, he asked for a bit of an introduction. So I'll start going into quite some detail about what evidence synthesis actually is and why we want to use it. I know that some of you are already familiar with these methods, so apologies if it's a bit slow for those of you who are, but for those who are not, I hope it will give you a bit of an insight into why we use evidence synthesis and its strengths and challenges. And then in the second half, I'll give a couple of examples from our work in the past on influenza. So clearly for any infectious disease, we, in order to control and prevent epidemics, we need to know about quantities such as prevalence, incidence, transmission, and severity. But these are characteristics that are rarely, if ever, directly observed. However, there may well be plenty of indirect information on quantities that can be expressed as functions of the key parameters of interest. And hence we may be able to estimate indirectly these quantities through the synthesis of different types of data and information. So typically these sorts of data come from multiple sources that may be sparse, they may be biased, they may come in the form of prior information from previous studies. And so what is Bayesian evidence synthesis? Well, it's a generalization of Bayesian inference, allowing the combination of these different types of data. And increasingly, this has been used not just in our group, but by lots of different people in infectious disease, not only in influenza, but also in other infectious diseases. Doing things, combining data, whether it's surveillance data or in some cases surveillance and genetic information. So just to give a brief background into what Bayesian inference is, again, apologies if you're already very familiar with this, but the idea is based on we have some prior level of knowledge about some quantity theta that we're interested in estimating. We wish to update that prior knowledge with our newly collected data, summarized by this function called the likelihood. And by combining these two, we get an updated posterior distribution for the quantity of interest theta given the observed data y. So in this very simple example, the red line gives you the prior distribution, which in this case is mildly informative. The majority of the prior mass lies below 0.5. In other cases, if you have no knowledge or want to express the fact that you don't know anything about the parameter beforehand, you might have a flat prior which says that each value between 0 and 1 is equally likely, for example. And then in this simple example, suppose we observe 2 out of 3 people experiencing the outcome of interest, and so this is quite weak information, so you see quite a flat likelihood, but by combining the prior with the likelihood, we obtain a posterior distribution which is less variable. It it's more peaked and is a compromise between the prior and the new data. So this inference can be represented by what's known as a directed acyclic graph, where the parameter we're interested in, theta, is here, and the double circles represent the fact that this is a parameter with prior information on it. The squares denote the observed data, and the solid arrows denote the fact that this is a distributional relationship, a stochastic relationship, in this case a binomial likelihood. Bayesian evidence synthesis extends this idea of Bayes' theorem to multiple sources of information. So, for example, now we have, say, n independent data sources from which we want to estimate k different parameters theta, some of which have, all of which have a prior distribution, which may be flat, uninformative, or informative. And these data may be a mix of data that directly inform a single parameter, for example, if psi1 is equal to theta1, and now these dashed arrows represent deterministic functional relationships, or the data may indirectly inform more than one parameter via a function. So in this case, psi j is a function of both theta1 and theta I, and hence, in combination with all the rest, indirectly informs both of these parameters. This is just saying the same thing, but in statistical terms, where, well, yeah, each independent data source provides information either directly or indirectly. And we want to conduct inference on the basis of both the direct and the indirect information. And this could be done in a maximum likelihood setting, where the likelihood is the product over each independent data source of the contribution from each of those. But we're going to be stick to being Bayesian here and include also the prior information. So to exemplify this, I'm just going to look at a very toy, simple example and use it to hopefully illustrate some of the key aspects of evidence synthesis. So suppose we're interested in estimating a basic parameter, lambda, which represents flu incidence. But what we actually observe, y1, is a noisy version of this mean lambda rho, which is the incidence multiplied by a reporting rate. Now, clearly, in this instance, if you only have these data and you don't have any prior information on either lambda or rho, then these two parameters are not separately identifiable. You can only identify their product, lambda rho. However, if you have prior information either from previous studies or from expert opinion, for example, on either lambda or rho, then we can identify both lambda and rho separately. If now we have further information from an independent study on, say, the reporting rate, in this case, then if there are flat priors on both of the parameters, then by using two different data sources, we can separately identify both lambda and rho. And then in the case that we have an informative prior on one or other or both of lambda and rho, we now come to the situation where we've got the potential for conflicting evidence. So ideally, if all the information from the priors and from the data are consistent with each other, then by including them all in the evidence synthesis, we will obtain posteriors that are more tightly identified, are less variable than if we use only some of the information. But clearly, if these, for some reason, perhaps because of biases that we haven't accounted for, or some naivety in the model assumptions, that the evidence is not consistent with each other, then clearly we have to reassess our model. And suppose now we have a third independent data source which gives us direct information on the instance. Now we have three data sources informing two parameters, and so we've got one degree of freedom for potential conflict, even if we've got flat priors on the parameters. And if we have informative priors, we have even more potential for, say, prior data conflict or conflict between the data sources. So this toy example illustrates the three key features of evidence synthesis. So in theory, the combination of all available relevant data sources should lead to more precise estimates in a principled way where all the estimates are consistent with all the evidence. However, when we do have multiple sources informing a single parameter, we've got the potential for conflict, and in cases where we have sparsity of data, some parameters may be unidentifiable without further model constraints. And so these two last bullet points give you the reason why model assessment and a cycle of model development and model assessment is particularly important in evidence synthesis. So two of the examples that I'm going to show you come from, again, the 2009 pandemic. And first of all, a model that we worked on to estimate transmission during the pandemic is basically a more complicated version of the toy example that you've seen here. So this is work that Paul did in our group. So it's an SEIR model that is embedded within an evidence synthesis. There's the infection model, then there's a disease model governing how the infections arrive in healthcare services, followed by a reporting model down here. And this model synthesizes information on serology, on GP consultations, confirmed cases, positivity data, as well as other prior information and data on, for example, contact rates and so on throughout the model. These were the 4 data sources that you saw in the previous slide during the first two waves of the pandemic. And observations, this is a discrete time model, and we define the number of new infections in terms of the incidence, lambda, and the susceptible population, S. The observation model treats GP consultation data as negative binomial, so with over-dispersion. The virological positivity data is treated as binomial, and the serological data also treated as binomial. And combining all these data together, we estimate an R0 about 1.65 in London during those first 2 waves. So the other example I'm going to go into a little bit more detail because it's the work I'm more familiar with, concerns the estimating the severity of the pandemic. And I'm sure all of you are very familiar with this pyramid picture and approach where only a proportion of the infections become symptomatic and a further proportion become hospitalized and a further proportion progress to either ICU admission or death, the 2 severe outcomes we're considering. And our aim is to estimate case severity risks, so the probability of a severe outcome such as hospitalization, ICU admission or death given infection. And the way that we do this is to recognize that these probabilities, conditional probabilities, can be expressed as products of component conditional probabilities of being at one level of severity given that you're at a lower level. And we might have information at each or at different levels of severity, which maybe in general could be considered as either Poisson or binomial, or if you were considering over dispersed data, some other distributions. And then the key assumption is that this pyramid structure, the fact that at one level the number of infections is binomial with the denominator being the number of infections at the level below. So our challenge is to estimate these case severity risks or symptomatic case severity risks using the multiple sources of evidence where most of these are either under-ascertained or biased or both. And the idea is that by combining lots of these data and accounting, hopefully, for some of the biases, by triangulation, as some epidemiologists call this, we are able to estimate without bias the severity risks. So a general model for severity, this is just notation, I'll skip over that. In fact, I've talked mostly about this. We have the number of infections at each wave, age group, and level of infection is binomial with the number of infections at the previous severity level for that wave and age group. The basic parameters of this model are the conditional probabilities of being at one severity level given that you're another, P, which we give on flat uniform priors, and then in particular detection probabilities, which describe the under-ascertainment or the difference between what we observe and the true number of infections at each level. The functional parameters are those that we're interested in the case for severity risks. So for the first two waves of the 2009-10 model, this is basically just a DAG which shows the severity pyramid again, and the data that we synthesized were included data on deaths, on hospitalizations, both directly on the numbers hospitalized, but also on the conditional probabilities of death or ICU admission given hospitalization, information that on the number symptomatic, which came from the HPA's estimates with a detection probability, and then serology information directly informing the infection attack rate. The model changed slightly for the third wave in the 2010 and 11 season due to changes in the surveillance data and available information. Some of the parameters we used prior distributions based on the first two waves. We also had we also took a two-stage approach where we estimated. We had two submodels estimating the number symptomatic and the number of ICU admissions, and the posteriors from these two submodels were then used in this second stage model. One of the key things which we wanted to look at when we were assessing this model was the sensitivity to the different types of data that we used in the first two waves versus the third wave. So we wanted to compare those initial results with what happens if we use a consistent data source, the RCGP data in all three of the waves on GP consultation. But note that the sample sizes were much smaller for the RCGP analysis than for the first two wave HPA estimates. And in terms of the estimates over the three waves, in black is the original model estimates using different data sources. In red is are the estimates using the consistent RCGP data source over the three waves. And so in terms of the case fatality risk, which is what's plotted here, you don't see too much difference between them. Where you do see a difference, particularly in the second wave, is in the denominator of the number of symptomatic infections, where the posterior distributions, particularly in the most extreme age groups, the under ones and the over 65s, differ quite substantially. So hopefully just from this sort of brief overview of Bayesian evidence synthesis, I've shown that the methods can be useful for combining multiple disparate, possibly biased data sources that accounts fully for the uncertainty in each data source, that minimizes selection biases, and allows a flexible framework for incorporating different types of information. And a lot of the work that we're doing now is summarized in trying to address some of the challenges in statistical inference, answering questions such as how should evidence be weighted, how should we handle dependence between data sets, in particular how to efficiently estimate such complex models. And my key area of interest, which is the model criticism side, the importance of understanding which sources of evidence are driving conclusions, and how to detect and measure consistency of evidence. So I'll finish there.
Thank you very much. But just my question is how you test the assumption to connect the different data set. I mean, basically, you're making some certain assumption. Mm-hmm. For example, I can give you the example. You're telling me you're combining data, you're reducing bias. Mm-hmm. But to me, that's introducing the bias. And also bias you're talking about, about the data, the collected data. This is the reported bias. It's different from what is the expected value could be.
So there are different ways. So and that's why I think model criticism, particularly for evidence synthesis, is such a big area of research in statistics. So you might use sensitivity analyses, for example, which we often do to assess your different model assumptions. So the idea about trying to account for biases, ideally we try and incorporate prior information to account for, say, selection biases into a particular population, if you have that from previous studies or from various possible sources. And obviously those sorts of, including those sorts of prior information, again, implies that you have to be careful about doing sensitivity analysis to understand the robustness to these types of prior information. And so it's very much, I see it as I see evidence synthesis as a way of being very explicit about what your assumptions are and how to assess them, and to hopefully use multiple data sources to come up with a model that gives you estimates that are consistent with all the available data.
Is there any other question? If there's no more question, I think we have lunch will be served in the same place as the coffee, so I'll be nearby. And I think we can come back in 1 hour, and then we'll have 3 more talks, and then a discussion. The next talk are more policy questions.